Our presenter for today's topic is Mr. Albert Luna. Albert has been a design engineer for the past 8 years, more than 3 of them with Interface. He holds an associate in science degree in automotive technology from Los Angeles Technical College and a bachelor in science degree in mechanical engineering from California State University, Los Angeles, where he was a member of the Pi Tau Sigma and Tau Beta Pi Engineering Honor Societies. Prior to moving to Arizona, he was awarded the Engineering in Training designation from the state of California. Joining us for our Q&A panel are Mr. Brian Peters and Mr. Scott Dunn. Brian Peters has a mechanical engineering degree from Arizona State University and has been with Interface for 5 years. He's currently a regional sales manager, and his primary market focus has been in the aerospace and oil and gas industries. Scott Dunn has been a production manager at Interface since 2000 and has over 2 decades of experience manufacturing load cells and scales. He has an industrial engineering degree from the New Jersey Institute of Technology. I'm going to go ahead and pass it over to Mr. Albert Luna without further ado, and enjoy the webinar.
Good morning, everyone. Thank you for being here. Today's presentation is Load Cells 101, and I will give a brief basic description of what a load cell is, and from there we'll move on to giving some information about where load cells are applied. And to avoid any, great. This is our agenda. I will be explaining some of the definitions, some of the basic terminology that is used in the load cell field. From there I will go on to explaining a little bit about load cell basics, also a little bit about strain gauges, and some of the internal processes that we do here at Interface to enhance the performance of our load cells, such as moment compensation, temperature compensation, and from there I will give a brief explanation about what takes place during the calibration process. From there, I will refer you to one of our pages on our catalog, so you can see where the different specs that the load cell needs to meet are, and make it easy for you to understand what those mean. Towards the end of the presentation, we will give an explanation about the different types of applications and how the load cell relates to those applications. And the last part of our session will be a Q&A session where my colleagues Scott Dunn and Brian Peters will assist with any questions from the audience. Definitions. So let's start with axial load. Axial load is the load that is placed directly on top of a load cell, and it's acting along the central axis of the load cell. The calibration is the step where we basically verify that the load cell meets all the different performance parameters that are specified for the load cell. The capacity refers to how much load or how much force the load cell can take. Creep refers to the change in the load cell signal that occurs while the load cell is under load and all other environmental conditions remain constant. Deflection happens when the load is placed on the load cell and is a deformation. The deflection is the deformation of the load cell under load. Eccentric load is a load that is not applied along the axis of the load cell. It is applied at a certain distance from the center axis of the load cell. Hysteresis, nonlinearity, and SEB or static error band are some of the parameters that need to be met during calibration. The output is the output signal that comes out of the load cell after a load is applied. Rated output is related to output, as I previously defined, and symmetry error is the algebraic difference between the rated output in tension and the average of the absolute values of rated output in tension and rated output in compression. And if you want a more an extended explanation of what these definitions are, you can go onto our website where we have those definitions along with a more complete list of other definitions. So what is a load cell? A load cell is a device that converts a force into an electrical signal. The signal is proportional to the load being applied to the load cell. The load cell is designed to measure compression, tension, or a combination of both loads in tension or compression. The load cell has no moving parts. Therefore, there will be no wear and tear between the main components of a load cell. What we have here is images that show you some of the different models that we manufacture here at Interface. On the upper left corner, we have the bending beam, and right below it is an SML model which works as a dual bending beam. To the right of that, we have two column style load cells. The one on the left is for higher capacities. The one on the right is one of our WNC models, which can handle capacities of 100,000 pounds or lower. More images about some of our other products, the S-beam and the load button, and these are typically used for much lower capacities. This here is the anatomy of a low profile load cell. In the center we have the hub, and the hub can have different configurations. In this case we have a thread going right across it. Around the hub we have the beams. The beams are the part of the load cell where the strain gauge is bonded to. The outer portion of the load cell, the outer circumference, is what we call the mounting ring. And connecting the wires between each other, we have the interconnecting wires. The upper section of a load cell is what is called the flexure. The lower part is the base. Protecting the strain gauges from the environment are the cans or the diaphragms. We have one installed on the bottom and one on the top. The one on the bottom is illustrated here. The one on top has been removed for clarity purposes. On the side of the flexure, we have the connector, which comes in different configurations. And part of the features of a base are the mounting rings, which are the locations along the base that mate with the flexure on top of that. In one of the previous slides, I talked about the main components of the load cell, and these are images of those components. The first one is the flexure, which is a load-bearing component. And the flexure is designed to deform under load. Right below that, we have the second main component, which is the strain gauge. The strain gauge measures the deflections of the flexure, and several gauges form what is the electrical circuit in a load cell. So the flexure deformation, the deflections happening in a load cell or in the flexure because of a load being applied is what changes resistance in the strain gauges. And I'll go into that in detail in a few slides up ahead. Sorry, moving on. So let's talk a little bit about flexure design. There are three basic materials that are used during load cell construction, and it all depends on the type of application and the capacity that the load cell is going to be used for. The first material is 2024 aluminum, which is used for low capacities, usually in the range of about 2,000 pounds and lower. The next material is E4340 steel, which is used for much higher applications. On the low end of that scale, it starts around 5,000 pounds and it can go all the way up to 1 million pounds. We also specify 17.4 stainless steel, and this material is typically used for hermetic or submersible applications. Two of the critical features of a flexure design are the thickness and the height of the beam. Those dimensions are determined in order to focus or to obtain a certain level of stress in the beam area or in the beams around the hub. By determining the proper thickness and height of those beams, we have the flexure. Let me rephrase that. So by careful calculation of those dimensions, what we do is we make those areas around the flexure the weakest part in a flexure. What that does, it concentrates the stresses in those beams, which make them the ideal location for strain gauge bonding on a flexure. Now let's give a little background about what a strain gauge is. Here we have this image which shows the different parts of a strain gauge. Number one is pointing to the grid lines. The grid lines is the pattern in the center of the strain gauge that is sensitive to the strains on a flexure. Number two is pointing to the end loops. The end loops help with creep compensation, and the amount of creep is determined by the length of those end loops. Number three is the solder pads. The solder pads is a point on a strain gauge where connections across the strain gauge are made. Number four is pointing to one of the fiducials. There are several fiducials around the strain gauge, and these help with gauge alignment on a flexure during the gauging process. And the last item, number five, is the backing. The backing serves two purposes. The first is to isolate the metal foil from the flexure, meaning that it prevents electrical shorts between the foil and the flexure. Also, its second purpose is to provide support for the foil material, and it is along the backing where the epoxy is applied in order to bond the strain gauge to the flexure. Here we have different types of gauges, and I'll give a brief explanation of where these are found and some of the which type of load cell these are used on. The first image is that of a linear type gauge. This type of gauge is used for bending beam applications, and these are typically found in some of our low capacity applications such as the MB cells. The second image is that of a shear strain gauge, which is typically found on the 1200, the 1100, the 1000 series load cells. Now the Poison, I don't know which gauge that is. That is a Poison gauge, and these gauges measure strains that are caused by normal stress applied or normal forces applied to a column type load cell such as the 2100 series. And the last image that we see here is what we refer to as the chevron type gauge, and this type of gauge is typically used for torque applications. These are found on some of our torque transducers, such as those in the 5400 series. So now let's talk a little bit about the Wheatstone Bridge. The Wheatstone Bridge is the electronic part or the electric element of a load cell. It is made up of 4 identical gauges. In this case, it can be made up of a combination of number of strain gauges, usually 8, can be made up of 16, but in this case I have 4 for clarity purposes. Now the Wheatstone Bridge, the way we get a signal out of the Wheatstone Bridge is by applying a supply voltage across the 2 excitation terminals. And the way we make this output signal vary is by changing the resistance in those gauges. In order for us to vary the signal coming out of the load cell, half of the gauges have to be under tension and the other half have to be under compression. So what happens is when a gauge is under tension, the resistance across that gauge will increase, and when the gauge is in compression, the resistance across that gauge will decrease. So how does the resistance across a gauge changes? So let's take, for example, a small segment of wire. If we pull on this wire, or if we put a tension load across along this wire, what we do is we reduce the cross-sectional area of this wire. The decrease or the change in cross-sectional area, the smaller the cross-sectional area will decrease the current flow flowing across this element of wire. So what we have is a condition where the resistance, the electrical resistance across that wire increases. On the other hand, if we have this segment of wire under compression, its cross-sectional area will increase, and therefore the current flow across this segment will increase. And what we have is a condition where the electrical resistance across this element has decreased. Now let's talk about how the flexure, how the formations on a flexure change the resistance across a gauge. So what I have here is an image, a cross-sectional view of a low profile load cell. The blue boxes in the beam area indicate the location where the strain gauge is bonded to the flexure. So because we don't have a load, in this case, we don't have a load applied to the flexure, what we have is a undeformed gauge area. And as I mentioned earlier, this area or these beams are designed to be the weakest points on a flexure. So what happens when we apply the load? Let's say we restrain the flexure from movement at the bottom section of the mounting ring, and we apply a load to the center of the hub. In this case, the way I have it drawn here is we are applying a tensile load, and what we see is the gauge area, those blue squares that I had previously illustrated are now being deformed, and what we have across those across what was once a square section is strain lines going across those sections. As you can see here, the right hand of the flexure is under tension, while the left side of the flexure is under compression. So if we focus on the gauge that is under tension, what is happening is that because of the grid lines, because of those grid lines being aligned in parallel with the strain lines that are occurring across the beam, what we have is those strain lines are putting that gauge in tension. Those strain lines are pulling the grid lines on the flexure. So what we have is a gauge that is under tension, and therefore the resistance across this gauge is increasing. Now let's take a look at the other side of that flexure, of that illustration. If we pay close attention at the superimposed image of the gauge across that beam, we see that the grid lines are not aligned with the strain lines. The grid lines are perpendicular to those strain lines, and therefore the gauge is under compression. And what we have is a resistance across the gauge that is now decreasing. So with this in mind, what I have here is an illustration that shows how the current is flowing across the bridge. If we take a look at the image on the left, and if we follow the flow of the current, we see that more of this flow, more of this current, once it is dividing itself across the upper branches of the bridge, we see that more of the flow is going across the gauge with the lower resistance. And what it's doing, because it's flowing from the positive side to the negative side of the bridge, we have a positive signal coming out of the load cell. On the other hand, when we apply a compressive load, we see a situation where the flow, most of the flow most of the current is going across the meter here from the negative side to the positive side of the bridge, and therefore we get a negative signal coming out of the load cell. So to explain a little bit about why it is about why we make our own gauges here at Interface, I'm going to bring Brian Peters for that.
Sure, Albert. Sorry about that. I unmuted a little too soon there. Had them in stereo. Not everyone may be aware that Interface makes our own load cell, or excuse me, our own load cells as well as our strain gauges. And the reason we make our own strain gauges, it provides several benefits. By doing so, we can thermally match the gauges to the material properties. And as a result, we don't need to use any mod resistors as part of our bridge. You get a simple Wheatstone bridge, and the benefit of that is very, very, very good temperature performance, very stable, along with a higher output. Many of our load cells are 4 millivolt per volt, and that can be achieved at lower actual mechanical strain levels of the flexure itself. So higher output means higher resolution, better signal to noise ratio, and more confidence in your measurement.
Thank you, Brian. Now let's talk a little bit about moment compensation. So after the flexure has been gauged, it has been wired, and some of the electric bridge has, or the Wheatstone bridge has been wired and properly configured. What we do is we do moment compensation, and the purpose for this is to reduce measurement errors due to eccentric loads. And how do we perform it? We basically put loading on the cell eccentrically, and what we do is we rotate this load around the flexure, and we are recording the output signal coming out of the flexure or out of the load cell. And after that, we basically compensate to minimize those errors based on the initial signal outputs that we are getting out of the load cell. So what I have here is a graph of the uncompensated condition of the uncompensated moment load cell. So as you can see here, we have a if we take a look at those values and we take the difference between the highest value and the lowest value, we get about I believe it's about 12 microvolts per volt of difference, which is in this case would be greater than our spec for moment for a specific model. And after the moment compensation is performed, what we have here is the same output signal, but now the error between, or the difference between the upper values and the lower values is much lower. In this case, is below 3 microvolts per volt. So now any eccentric loads being applied to the load cell, the error induced into our signal because of that is much lower. Now let's talk a little bit about temperature compensation. It's another procedure that we perform on every load cell that reduces force measurement errors due to ambient temperature changes. And how is it performed? It is performed by recording the output signal at a cold and a cold and a hot temperature, basically a temperature lower than room temperature, and a second temperature that is higher than room temperature. In this case, between 15 and 115 degrees Fahrenheit. Now, what's important about performing this procedure is that there is no load being applied to the load cell. We have the load cell under a no load condition, and what we're doing is just recording the output that we're getting out of the load cell as we put the load cell through a temperature cycle. Once we analyze those values, then we determine how much compensating wire we need to add to the bridge in order to minimize those temperature-induced errors. So what we have here is a graph of three load cell conditions. The upper red line is the uncompensated condition where the load cell has been put through a temperature cycle, and we see errors in the magnitude of about 12 microvolts per volt. Sorry, in this case, about 12 pounds of error that has been induced to our measurement because of the uncompensated condition. The second case, the blue line, is a load cell that has been compensated. However, the compensation took place between temperatures that go from room temperature up to a hot temperature. And we can see that the error has been minimized. However, we still have about just over 5 pounds of error that are induced to our measurement because we have not done a compensating procedure that goes from a cold to a hot temperature. The third condition is where we have fully adjusted the temperature-induced errors or compensated for the temperature errors induced to our signal. We have compensated from a low temperature to a hot temperature, and we can see that now we are keeping our error to under 4 pounds. We have reduced the magnitude of that error to under 4 pounds. So after temperature compensation, after moment, what we do is we basically run the calibration procedure procedure on every load cell. What I have here is an image of a typical calibration setup. We place a load cell on top of a standard, and then we take measurements. We take the measurements of the output signal of the load cell. And there are 3 critical parameters that need to be met before we are done with the assembly procedure of the load cell. They are the hysteresis, the nonlinearity, and the static error band, or SEB. So what we have here is an image of the specifications that you would find for 1200 series models, and we have highlighted the parameters that are critical for during the assembly of the load cell. For easy reference, we have these values highlighted, and you can see that based on the model that is being used, we have to meet those parameters before the load cell leaves our facility. And here, for easy reference, you can see that on the upper left corner, we have the parameters for the SEB, for the nonlinearity, and for the hysteresis. Also, right below those, you can find what the specs are for the creep, what the values should be met during creep compensation, and also right below that, you see the specifications that we need to follow in order to have our load cells meet the eccentric load sensitivity. Further below, around the middle of the page, you see there the values, the rated output values for the different capacities. And below that, further down below, you see the amount of deflection that is happening across the load cell because of the load at capacity that is being placed on top of the load cell. Now let's talk about some of the applications where you would typically find load cells. And to assist me with with that explanation, here's again Brian Peters.
Thanks, Albert. Oil and gas applications can vary quite a bit. The one in the picture there is actually a pump jack application, and load cells used on that to give feedback to the control system that basically tells the pump jack to turn on or turn off depending on when the well is ready to be pumped. Other oil and gas applications include line tension monitoring. That can be done with low-profile load cells like we saw, maybe some load pins. There's different ways to get that measurement. Also, downhole applications exist where you may need to be able to monitor the axial, the torsional, or even the bending moment load that can develop in downhole tool strings. Very, very deep down under the Earth's surface. There's some other challenges on those applications there. Other popular application would be hook load monitoring. That's basically another line tension type measurement. Those are a little less intrusive though in the structural system. Some other applications where you're going to find load cells, material testing. This is pretty self-explanatory. Load cells, heart of these systems. The load cell is going to give the software that's on the machine the feedback to know exactly how hard the specimen is being pushed or pulled, and then also most likely give feedback to control that loading mechanism. So load cells are usually one of 2 measurements that are made on these machines, the other typically being a displacement measurement as part of the material test process. Aerospace. Aerospace is a very strong industry for interface. Every airframe component, whether it's the entire structure or wing assembly, even the landing gear component, needs to be tested very thoroughly, not only for design strength but also from a fatigue standpoint. And load cells are used there in conjunction with hydraulic actuators to not only give the test signal back to the data access system, but also typically to control the hydraulic load, again similar to the material test frame that we saw earlier. But as you can imagine, these airframes get cycled millions and millions and millions of cycles to ensure that the plane's stay up in the sky. So, some challenges exist there to ensure that the load cells will endure the fatigue cycles, and also will often supply multi-bridge load cells, where you have several discrete bridges on the sensor so that you can have individual signals, again, running to DATAC or to the hydraulic control system.
Thank you, Brian. And with that,